Cool. Let's discuss problem number 2. Problem number 2 is going to be correlation of error terms. Correlation of error terms. Okay. Correlation of error terms. So one of our biggest assumptions of linear model is the error terms. If you remember well, error terms E1, E2 for the different observations, we say the error terms, they are uncorrelated. That was our assumption, right? We said these are uncorrelated. They don't care about each other. They are uncorrelated, not related in any way. So the fact that E2 is positive provides us no information on E1 or E3. It doesn't matter, right? That's what it means to be uncorrelated. But then, what we might find is they might be correlated. How does it affect? Let's see. So you remember that our standard errors that are computed, the standard errors that we compute for our BJs, for our estimation here, they are based on this assumption that our error terms are uncorrelated. Correlation will lead to narrower confidence intervals. If confidence interval, it will affect our standard errors, right? It will affect our standard errors, and our standard errors are used in building confidence intervals. So correlation will lead to wrong standard errors. How is it going to be wrong? It's going to lead to narrower confidence intervals. You remember there we had our BJ, our estimate, and we said so it's going to be a lower and upper limit that house the correct BJ, right? Correlation is going to affect our standard errors in such a way that this region where we know, let's say 95% probability that the true BJ is going to lie, is going to be narrower. It's going to be narrower just because the errors are correlated. It's going to be narrower confidence intervals and lower p-values than they should be, right? It's going to be lower p-values for these BJs for our estimate. When we plot our table, when you come up with a table, it's going to lead to lower p-values than they should be. So what that means is if there are lower p-values than they should be, we might end up including in our model BJs that are not significant. Correlation has lied to us. It has made the p-values significant. They are lower. It has made them significant. So now we are going to start choosing coefficients that are not even needed in our model, right? Correlations correlations here among these error terms, it has created a fake model for us, right? The correlations among error terms, they happen frequently in time series data. Where you observe measurements at discrete points in time. Let's say for every hour you measure your heart rate, or you measure whatever it is every single hour, or let's say your heart rate, your stock price, whatever, every single hour, right? What you might find is that points that are adjacent to each other will be positively correlated. That is a normal result. That is a normal consequence of our time, or that happens due to correlation in time series, right? What you can do is you can plot your residuals and see if this is a case. Like if you plot your residuals, let's just say residuals. You're going to plot your residuals, and let's just put time. Let me just say time. The hour. So you're going to have a residual for 9 a.m. and you're going to have a residual for 10 a.m. whatever. Usually what will happen is when you plot the residuals, adjacent residuals will have usually values that are close to each other. If you see such a pattern that the residuals have values that are close to each other, it might be proof of there being correlation in the error terms, right? Proof of correlation in the error terms if the values of the residuals that are adjacent to each other are close or they're equal, right? Cool. So that is one area that you can come across, correlation of error terms. Some of these problems we're going to solve them later in later chapters, but for now we're just introducing them because they are relevant to this chapter. In the next chapter, in the next video, we're going to discuss problem number 3.